Hi Math 215 students. In this video I want to say just a few words about the proof of the invertible matrix theorem, which is the big part of section 2.3. So here we go. Now, this is not a class on proving things, but there are a couple ways this will help. So here are the outcomes we will see. These were listed in a previous video, but we're going to repeat them here. And here is our invertible matrix theorem. We saw this in the last video. The following conditions are either all true or all false, and they have to do with whether your matrix A has an inverse or not. Now, we have not in this class so far made a big deal about the proofs of the different theorems we've seen, and we're not going to make a super huge deal about this proof, but there are some interesting ideas in it. So I want to kind of talk about them. All right, so first off, the statement of the theorem begins with this line. Say A is n by n, the following statements are either all true or all false. And that's followed, of course, by a long list of statements. Now, this kind of theorem, where you're saying that a bunch of things are either all true or all false, often appears with different language. You can see it sometimes in some math texts as the following are equivalent, and then you'd see a long list of statements like the one we see here. Both of these are the same thing. What they mean is that no matter which statements you're looking at, if one of them is true, then they're all true, or if one of them is false, then they're all false. So to prove something like this, where there are multiple statements, you're going to need to prove if A, then B for every pair of statements. So if A were the first statement in the list and B were the second statement in the list, you need to show that if A is true, then B is true. If A were the last statement in the list and B were the second statement, you would still need to show that if A, then B is a true statement. All right, so again, this class is not necessarily about proving things, but there are some interesting ideas here. And certainly if you take a look in your text, you're going to see this sort of structure in the proof of the invertible matrix theorem. Okay, so let's take a look at what else we see in here. Here is our list of statements about invertible matrices and linearly independent sets and spanning and so on. If we were to kind of take a look at these statements and kind of point out ones that are useful to us, well, actually, we would do this, if we looked in the textbook at the proof of this, you'll see some common features in different parts of the proof of the invertible matrix theorem. So please open up your textbook and take a look at the paragraphs of proof that follow the theorem statements. What our proof does in many places is it uses this property of transitivity. If you have the statement, if A, then B, and if that's a true statement, and if the statement, if B, then C is true, where A and B are different mathematical conditions, then automatically you know that if A is true, then C will also be true, all right? So hopefully you can see the pattern here. We have if A, then B, if B, then C, and we're kind of linking these two. If A is true, then B has to be true, but if B is true, then C is automatically true. So we can conclude that if A, then C is also a true statement. All right, in math we like to use symbols to shorten things. A implies B means pretty much the same thing as if A, then B. B implies C means the same thing as if B, then C. And what we're saying is that if both of these statements are true, then you can conclude, or what is implied, is the statement A implies C. Okay? Now, in the proof, what you'll see in particular, as you read through the paragraphs of proof, there is some effort to show that statement A, that A is an invertible matrix, implies statement K, that there is an n by n matrix D such that AD is equal to I. And then K implies statement G, that the equation AX equals B has at least one solution for each B in Rn. And then G implies A is also shown there. Now what this means, because we have this transitivity rule, if A implies K and K implies G, if A is true, then we know that K is true. And if K is true, then we know that G is true. So it would also be true to say that if A is true, then G is automatically true. Okay? Similarly, if K is true, and since K implies G and G implies A, if K is true, then A is automatically true. And if G is true, then by transitivity, K is also true. So if any one of these three statements is true, then the other two will also be true as well. Now, it's also the case that if one of these is false, you can say something. So if A is false, we certainly can't conclude K. But what we can do is take a look at this arrow here. We know that if statement G is true, then statement A is automatically true. So if A is not true, if that's not the case, then it cannot be the case that G is true either. Because if G was true, we would know that A is true. But that's not the case. A is not true. So if A is not true, we can automatically conclude that G is not true. And if G is not true, we can similarly conclude that K is not true, going backwards along that arrow. And if K is not true, we can conclude that A is not true. All right, so as we take a quick look back at that statement, the following statements are either all true or all false. We see that happening already here. Statements A, K, and G are either all true or all false because we have this relationship shown there. Okay, here is another part about transitivity. We saw this kind of on the last slide, but it's also the case that in your proof you see kind of this figure here. If statement A is true, then that implies that statement J is true, and there's a sentence that describes why that works. If statement J is true, then statement D is automatically true, and your textbook contains a sentence explaining why that's true as well. And then similarly, we have justifications for each of these other arrows. And as you look at these statements, they're arranged in sort of a cycle of implications there. All right? Now, these are the statements themselves that you'll find in the proof of in the statement of the invertible matrix theorem, but their proof, at least as it appears in the textbook, is done in this way. We use the truth of statement A to prove the truth of statement J, and then from J we prove the truth of statement D, and so on through C and B as well. Now again, just like on the previous slide, if A happened to be false, then we know that B can't be true, because if B was true, that would imply that A is true, and we know that A is false. So if A is false, then B is automatically false, which would mean that C is automatically false, which would mean that D is automatically false, and so on through J. And so, again, we see sort of this pattern because of the proofs that are given for each of those steps. The statements are either all true or all false. Now, at this point, we have statements A through L to deal with, and we've only really touched A, K, and G, and A, J, D, C, and B. So there are definitely more statements to link up in this way. So we'll keep visiting some of those ideas. All right. Now, for some of the statements in the invertible matrix theorem, you'll see a proof of this form. A is true if and only if B is true. And you can say that if you have proved that if statement A is true, then statement B is true, and you have also proved if statement B is true, then statement A is also true. Now, these things don't necessarily automatically imply each other. If-then statements come with an order to them, and if you change the order around, you're not guaranteed to get a true statement. But if you can find a reason why, if A then B is true, and if you can find another reason why, if B then A is also true, then we shorten that in math and we often say A is true if and only if B is true. In symbols, we draw an arrow from A to B, but also one from B to A. So we have sort of a double-headed arrow showing that if and only if relationship. Okay, now again, we're not going to dive into the details of the proof, but if you look in the textbook at the paragraphs of the proof, you'll see that these statements here are all kind of linked in this way. Statement A is true if and only if statement L is true. Statements D, E, and F all sort of imply each other, or E implies both of the others, and each of the others implies E. And similarly, H implies G and I and G each individually imply H. So these are examples of what we call if and only if statements. Now, again, for each of these statements, if A happened to be false, then there's no way L could be true because we have that relationship. If L is true, then A is true. So if A is false, then L is automatically false. And similarly, if one of these statements, D, E, or F, happen to be false, we could conclude that the other two are false as well. So they're either all true or all false because of these relationships that the proof establishes. Okay, so you might ask, if we are done yet, have we proved that these 12 statements are either all true or all false? And as you take a look at it, well, we need to kind of summarize what we've done so far. We started off by showing that A, K, and G implied each other in this way. We just got done talking about biconditionals, A and L, and G and H and I, and D, E, and F. As you hook those things up, you'll see that here is a picture of how those statements are related to each other according to the proof given in the textbook. And if you were to ask, what happens if statement I is true, can we conclude that statement F is also true? And as you take a look at that, well, we'll just see. If I is true, can we follow the arrows of implication to get to statement F? If I is true, then H is true. If H is true, then G is true. If G is true, then A is true. If A is true, then J is true. If J is true, then D is true. If D is true, then E is true. And if E is true, then F is true. So yes, if I is true, this chain of implications establishes that statement F would also have to be true. Okay, now remember, if we're proving an if and only if statement, we said that you have to show that if one of these statements is true, then any other of these is also true. So if I wanted to give a complete proof of this, I would need to prove that if I is true, then F is true. And so far, those steps that we've established and hooked together in this way do that for the pair I and F. If you wanted to, you could take any other pair of statements in this map and sort of say, can I get from anywhere to anywhere else following the arrows? Can I get from L to C? And the answer is yes. L implies A implies J, which implies D, which implies C. So yes, the truth of L means the truth of C. Okay? Now, as you take other pairs there, you might pause the video and just check the map. You will see that if any one of these 12 statements is true, there is a proof in the textbook, or a bunch of proofs that will allow you to conclude, because of these arrows, that the other statement you chose is also true. So this is actually a proof that these could be all true. Now you might ask, what about falseness? If statement D is false, is it automatically the case that statement G is also false? Well, if we take a look at where D and G lie in this map, let's remember that trick we said before. If statement D is false, then statement J cannot be true, because if J is true, then that would make D true, but we know D is false. So if D is false, I can backtrack along that arrow and conclude that J is false. And for the same reason, I can conclude that A must be false. And if I backtrack along that arrow, that would tell me that G can't be true, it must be false as well. So if D is false, then yes, G must also be false. And if you were to take any pair of statements here, you'll be able to establish that same relationship. And so that's what would happen if any one of these statements were false. You would be able to conclude that they happen to all be false. Okay, now let's take a quick look at an example of this. Statement D is the statement the equation AX equals 0 has only the trivial solution. Now, AX equals 0 means this. You've got your matrix A. We're multiplying it by a vector and getting the 0 vector out. Now, we certainly know that you can multiply the 0 vector on and get the 0 vector out. That's what's called the trivial solution. Now, if this is the only solution, or for X, well, that's what we're talking about. If statement D is false, then no, this won't be the only solution. There should be another vector I can multiply this matrix by and also get the 0 vector out if statement D is false. And it turns out that in fact there is. If you take a quick look, the first and second columns added together actually equal the last column. So if I were to take -1 times the first column, -1 times the second column, and add them to 1 of the third column, that would create the 0 vector. Okay, so then what does that mean? Well, our invertible matrix said these statements are all true or all false. If I know in the specific example that D is false, then is it automatically the case that G is false? Well, it should be. If D is false and these are all true or all false, if D is false, we can say that G is false as well. G is the statement the equation AX equals B has at least one solution for each B. Now, the matrix A in these two is supposed to be the same. So we're looking for, does A times something equals B always have a solution? Is there always at least one solution for each B? We suspect the theorem tells us actually that that should be false because this thing was false as well. But if we were to check this, what I'd be interested in is there a solution to this matrix vector equation? Now, if I were to solve, I would set this up using an augmented matrix probably. I put this as the final column attached to a column of these. And as I row reduce that matrix, here's what I'll end up with. I'll end up switching the first and second rows just to get the pivot position in the top row. But then as you use these two rows to eliminate the 1 in the bottom row and the 3 in the second position, you'll actually end up getting a row where you have all zeros except a 1 in the final column. And we know that if you have an augmented matrix in reduced echelon form, having a 1, having a pivot position in that last column tells you that there should be no solution to this. And so, in fact, the equation AX equals B, where A is this and B is this, does not have at least one solution. There's no solution. Okay? So, what I'm hoping you'll get out of this last example is that these two statements don't necessarily have anything to do with each other, at least not at first glance. But the invertible matrix theorem tells us that these properties all come together with a matrix. If the matrix is invertible, then all of the rest of these are automatically true as well. There's a proof for it. It's a long proof in your text, but it's there. And if any one of these happens to be false, then they actually all happen to be false as well. We can use sort of going backwards along the arrows in this map to justify that. Well, with that, we'll end our discussion about the proof of the invertible matrix theorem. Here's that list of outcomes again. If you have any questions, please let me know. But otherwise, I will see you in the next video. Thanks.